Good evening, folks, and welcome to the Advent of Code C++ live stream. My name is Craig, and tonight, as every night, we are going to be solving the new Advent of Code puzzle drops in C++, or at least doing our best to. Thank you all for watching. If you're watching the live stream on Twitch, you can check the channel description, and there you're going to find links to my YouTube channel where we have replays of all of these streams, plus links to the GitHub repo where I upload all of the code that we write in these sessions. If, on the other hand, you're watching the replay later on YouTube, you can just look in the video description right down there. You're going to find links to the Twitch channel for the live streams, and once again to that GitHub repo where all of the code lives. So, last night we had a puzzle that was based on pathfinding, trying to find the lowest risk, or really the lowest cost path through kind of a maze, sort of. But, and the solution that I got in part 2 last night for the big, blown up grid worked sort of okay. It took about 13 seconds, I think, to run. And which is not outrageous by any means, but I went back and I kind of fixed it up afterwards because I realized, this is really just a pathfinding problem, so we can use classic pathfinding algorithm, which is A star. So if you're not familiar with it, actually, I'll just bring up the page on Wikipedia here and show it to you. The A star search algorithm is a good description of how it works and, some pseudocode for it here. But basically what I did is I went back and I wrote this A star routine and I made it a library in my util directory just so that we can reuse it for other stuff. And the basic idea of A star is that, like we had in our original solution last night, we keep track of the cost to reach different nodes, which in this case are just, like cells in that grid. But it doesn't have to be a grid. It doesn't have to be regular space. You just have to have locations, which are nodes, and a way of determining what's adjacent to a node, which in this case is just going cardinal directions around a point. But again, can be anything. And the cost for those. So the cost is just the risk value of the node. So, like I said, A star works on a graph. It can be directed or non-directed. It can have any kind of cost function as long as the costs are always positive, or are actually greater than or equal to 0, I think works too. But yeah, so to do it with this case, I just, wrote up this A star function here. You'll notice it's templated on a lot of things. It's templated on a node and on a function that gets the nodes that are adjacent to a node and on a function that gives the cost for going from one node to another. So this is super generic so that it can be used with all kinds of graphs. And we might even find that we reuse it on another puzzle this year. Or if not this year, next year. Who knows? But the basic insight of this is that, yeah, you want to keep track of the costs to reach various nodes that you've been to. I'm not going to go through the whole detail of the algorithm. The Wikipedia article is good if you need that. But the key insight really is that you want to visit the lowest cost nodes that you know about first. So that's why we have this node queue here, which is a priority queue. And then we just sort that by the lowest cost. I know that, we have the sort for greater here, but normally a priority queue gives you lowest first, so we need a comparator that returns greater, and then it will, it'll give the highest first, rather. And so if we give it a comparator that returns greater, it'll give us the lowest cost first. So it's like a double negative. We got to flip it both ways. But anyway, the way that it works is if we haven't reached the goal, if we do reach the goal, we know the cost, and we can, do this backtrack path to figure out the whole path to that node. But otherwise, we look at all the nodes that are adjacent to the node that we're looking at. We figure out their tentative cost, which is the cost to get to the current node, plus the edge cost, the cost to move from the current node to the next node. And then if that calculated cost is less than the cost that we already know for it, or if there is no known cost for it, then we update it, and then that next node we put back on the queue. And so it's a best first search algorithm. And then I just adapted the day 15 solution to use it, and you can see here it's super simple. We have that blow up grid just like we wrote it before, but now we just say we want to get from the origin to this goal point at the bottom right. We give it this first function to tell what points are adjacent, which are just points in the cardinal directions filtered to make sure that they're on the grid. And then the cost function, just look it up in the grid. And that's it. A star, perfect. And it's about 10 times as fast as the solution that we originally had. I realize I'm talking through this kind of quickly because we don't have a lot of time until tonight's puzzle unlocks. In fact, just a few seconds. So we are just about ready to get into it here. Let's see what tonight's puzzle is. Packet decoder. As you leave the cave and reach open waters, you receive a transmission from the elves back on the ship. The transmission was sent using the buoyancy interchange transmission system bits, a method of packing. Okay. We've got transmission in hex. Convert hex into binary. Each character of hex represents 4 bits of binary. Okay. Bit transmission contains a single packet at its outermost layer, which itself may contain other packets. So we can have like nesting of packets. The hex representation of this packet might include a few extra 0 bits at the end. These are not part of the transmission and should be ignored. Okay, so we're parsing a binary format here, something I have a little experience with. Every packet begins with a standard header. First 3 bits are packet version, next 3 bits are the type ID. These 2 values are numbers. All numbers encoded in any packet are represented as binary with the most significant bit first. Okay. Packets with type ID 4 represent a literal value. Literal value packets encode a single binary number. To this binary number is padded with leading zeros until its length is a multiple of 4 bits, and that's broken into groups of 4 bits. Each group is prefixed by 1 bit, except the last group, which is prefixed by a 0 bit. This sounds a lot like variant, which is used in protocol buffers, if you're familiar with that, except instead of groups of 4 bits, that's groups of 8 bits. But, oh, it's groups of 5 bits. Okay, instead of 8 bits. Mm-hmm. Okay. So we get version, we get type, we get, okay. This packet represents the literal value with binary representation, which is 2021 in decimal. Okay. Every other type of packet represents an operator that performs some calculation on 1 or more subpackets contained within. Right now, operations aren't important. Focus on parsing the hierarchy of subpackets. Operator packet contains 1 or more packets. To indicate which subsequent binary data represents its subpackets, an operator packet can use one of 2 modes indicated by the bit immediately after the packet header. This is called the length type ID. So we can get length either in bits or in number of subpackets. Whew, okay. Kind of complicated, but we're basically writing a bit stream parser for this. So it's giving us an example here. Yeah, giving us more examples of the format. Parse the hierarchy of the packets throughout the transmission and add up all of the version numbers. an operator packet version 1, which contains an operator packet version 5, which contains a literal value. Okay, let's get our puzzle input and get to work on this parser. I have written some truly heinous binary parsers in my day, but I will try and make this one. I will try and err on the side of simplicity here. So we'll say hex string equals read file, and we'll use argv1 there as the first input to the program, and then I think we can let's think about the things that we have to represent. So we'll say there's a packet and there is a we'll use uint8t for these because these are just going to be 3 bits each, but there's going to be version, there's going to be type, and there will be, it'll either be a literal packet with type ID equals 4 or an operator packet that will contain some more stuff. So this will either, we'll use variant to represent this. So either it will have a literal value, which, is there any upper length limit on the literal values? Single binary number. Just that it's groups of 5 bits. So just out of an abundance of caution, we will use uint64t to have plenty of space for that kind of number. And then we will, the other thing that it can be is just an operator packet that contains more subpackets. So, and the length can be written a couple of ways. So total length in bits of subpackets or number of subpackets. But either way, it's going to have subpackets. So we'll use a vector of, well, we you know, we can't make packet recursively store itself in a vector like this unless we use some indirections. So we'll use unique pointer of packets to put those on the heap. So now we've got to parse packets. So we've got our hexadecimal string. We really want it as binary. So actually, I'm gonna write another helper function which is just going to translate that hexadecimal string into a vector of bools. So we'll just call it like binify. And we'll just say for C in hex string, we are going to put, we'll say, the value is equal to, well, let me look at the ASCII table just to make sure that these things are in an order that makes it easy to parse, and of course they are not. So, I don't know. This is... Yeah, we'll just go ahead and switch. Well, say if C is greater than or equal to the 0 digit and less than or equal to the 9 digit, we'll say that the value is C minus 0 digit, else if C is greater than or equal to capital A and C is less than or equal to capital F, we will say val equals C minus A plus 10, which will give us that value there. Otherwise, we should check fail because we didn't parse correct. It's not one of the expected digits. And we can say then do another check that val is less than 16, and then we can just get the 4 bits out of val that we expect. So we can just say and we should have a vector here. We'll call that binary, and we'll say binary dot pushback, and so we'll say val and 8, 8 being the 4th bit. If that does not equal 0, and we got to parenthesize this properly. So that's going to be the first, most significant bit, and then we'll do this similarly for 421, and we will have extracted all the bits out from that character, and we'll have our nice vector of bools to treat as our binary string. So if we were writing something that were like really highly performance oriented, then we would maybe like chunk this and do something different. But just having a vector of bools where we can consume however many bits we want is going to be useful. So next we have to just write our parsing routine. And this is going to be recursive, and I'm wondering what the best way to do this recursively is. That maybe yeah, this is how I'm going to do it. So the way that this is going to work is I'm using this unique pointer here. We're just going to allocate the packets on the heap owned by unique pointers, because that's going to make it easier to embed packets in other packets. And I'm going to, so we'll say, packet for that, packet. And the other, they'll default to null pointer. We don't need that. And the other thing that we're going to have is an iterator that on that vector of bools that points to just after what we parsed. So so that we'll know where we are in the bit stream and we can continue on going. So so we'll have this parse function return packet and iterator, and we'll have it take as its inputs begin and end just from a range within that vector. So now to do the actual parsing here, we should be getting. I'm referring back to the puzzle description here. The first 3 bits are the packet version. So we should be able to, so first of all, we'll check begin does not equal end. And we'll say check end minus begin is greater than or equal to 3 to get our 3 bits for the packet version. And we'll also declare our results here. And result dot packet equals make unique packet. Okay. So first thing to do is check that we have 3 there. So what we will do is say that packet the version part in packet is going to have 3 bits that are the first 3 bits in the stream. So we'll say the question is, can we be guaranteed these will evaluate left to right? That's a good question, but we'll find out. Multiply by the value of begin plus plus. I'm going to parenthesize that just to be maybe a little extra paranoid. So basically, we'll do 421 for those 3 bits. Then that we'll have our version. The next 3 bits are packet type ID. So we'll again check that we have at least 3 bits available. And it will be the same thing to extract 3 bits. If the type ID is 4, then it's a literal. Else it is an operation and contains more packets. So for a literal value, binary number is paired with leading zeros until its length is a multiple of 4 bits. Okay. So let's write. So I'm going to write a little helper function here. That's just parse literal, and actually we'll use a pair here. So it's going to return the number that it parses and an iterator past where it ends. And it's also going to take these begin and end iterators. I don't think we actually need to use type name there to qualify it. No, we don't. Okay. Okay. So, we'll start with an infinite for loop here, but you know, we'll break out of it when we actually hit our termination condition. So each iteration of this loop, end minus begin, should be greater than or equal to 5. Terminate it. We're going to terminate the loop if the first of those 5 bits is 0. And then we just need to assemble the next 4 bits. So we'll say value, we should have initialized that to 0 up here. But we're going to shift value left by 4. And then we're going to put in 4 more bytes of value. So So 8, 4, 2, 1. If we've hit our termination condition, then we will return the value and the current value of begin, which is now after all of the bytes that we've read. Otherwise, we'll continue and read another 5 bytes and keep going. So if value is 4, then we will result.packet type. We'll say begin auto literal after literal equals parse lit from that begin and our end there. So then we can begin is going to become that after literal, we're advancing that, and the packet contents are going to contain that literal that we just parsed. And that's not liking that because cannot infer that. Can't infer that. That's the uint64t. All right. Well, I don't know why it couldn't infer that, but there it is. Okay, so we've got that. We've got the literal parsing here. Right now, I'm just going to put a check fail here for the operator parsing. And just as a safety check, I'm going to take that the first example of a packet they gave us, which is a literal value, and paste it in as a test file and just see how our parsing works on that. And let's see what, okay. I think we are good to go. And we will just do test.txt. Well, actually, we haven't even done anything with this yet. We'll say then standard vector bool binary equals binify that hex string, and then parse binary.begin to binary.end, the iterators over the whole thing. And then we'll just do some checks here to make sure that it matches that. So the packet version ID actually, we shouldn't have underscores on these because it's a struct. Well, I'm not going to change those all right now just for that. But we'll say the version should be 6. The type should be 4. And the value the engaged index of that should be 0. And finally, the uint64t value held in contents should be the number 2021. Okay. Let's go ahead and run that on that test input and see. Okay, we've gotten to a check fail. So it is in parsing the hex string. I wonder if it's because there's a terminating new line that we read in. So we'll just see if C is the new line character. We'll just say yeah. It's the new line character. Continue and do nothing. Let's see if that fixes that parse error at least. Nope, we just got down there. So oh, that's not that was not the actual example that they gave us. That was the annotation of fields in the example. Because, of course, those aren't all the right letters. I should have noticed that earlier. Yes, the hexadecimal string is much shorter. That should be it. Now let's run it. Legal instruction. Wow, we really... let's make a debug build, and I will probably access some out-of-bounds memory here. Ooh, 79. Not return void in all control paths. Oh, of course. We didn't actually return the result, did we? Okay. So we got the version right. We got the type right. Let's go ahead and print out what it thinks the contents are here. Because I guess our binary number parser is not quite right here. Thinks it's 7. Well, that is not right, surely. We don't terminate if it's 1, we terminate if it's 0. So we had the termination condition screwed up. I bet that backwards. So that, yep, there we go. 2021, we are good as far as that goes. So we can parse literal packets at least. Now we need to parse operator packets that contain other subpackets. So if we have type ID other than 4, the bit immediately after the packet header is the length type ID. If it's 0, then there are 15 bits that represent the total length in bits of the subpackets contained by this packet. You know, I'm actually getting to a point now where I realize, you know, we've done this, we've like exploded this out for 4 or for 3 in different points, but I'm now getting to a point where I think that we need to make this a little more generic. So we'll just say we'll say yeah. and we can just give it a range over iterators on that vector. So let's just say a vector of bool considerator begin to end. And iterate through all these. So the result, we will left shift by 1 bit. And if that bit is set, that begin bit is set, then we will OR in 1 bit in the least significant bit there. Return result. And this is going to be useful for us in other places as well. And we can say, and then, value equals value left shifted 4. We parse bits from begin to begin plus 4, begin plus equals 4 there. Here we can, say begin to begin plus 3. And after we do that, advance begin by 3 there. Exact same thing down here. We'll go ahead and run that program again, but basically what that is, yeah, and all the checks passed. So what we can do with this now is get our length here. So check that we have at least 1 bit remaining there. We'll say length as subs is the value of that next bit. If length as subs is not true, then we have 15 bits that represent the total length in bits of sub packets. Say sub packet bits is we'll have to check minus begin is greater than or equal to 15, but the number of sub packet bits will be what do we call that? Parse bits. From begin to begin plus 15. So we'll read the next 15 bits in parse bits, and then we will advance that iterator by that same number. Now I'm beginning to think that maybe we should have made that a mutable parameter, that maybe we should have made that a mutable reference so that, it modifies it for the calling environment. Actually, that, I don't know. Modify non-const references still creep me out a little bit. But yeah, so we'll get the number of subpacket bits, and then we'll parse the bits in that range, but otherwise we'll use 11 bits to calculate the number of subpackets. $11 there. Now, the next part, which is the tricky part, is that we need to actually parse out those subpackets. So well, in either case, I guess we'll put them in the results. So we'll say, I think the number of subpackets is going to be slightly easier, so I'm going to write that one first, but we'll say for Unit64T subpacket num 0 subpacket num is less than the number of subpackets plus plus subpacket num. Then I realize a cleaner way to do this would have been just to, like have something that just yields the bits instead of having to keep track of these iterators, but we're writing this in a very STL-like way, so c'est la vie. We will get a packet and iterator by calling parse on begin and there. We'll update begin to equal subpacket result.after, which is going to be right after everything that we parsed out of the subpacket. And we will put in our result that we're building up. Well, we'll just put the vector here, and then we'll put in the contents at the very end. So so I have a vector of unique pointers of packets called subpackets, and then here we will say subpackets dot in place back. We'll move the packet from that result, and should be everything we need there, although I'm realizing now that we've only done result dot after definitely needs to equal begin in this case. And we can get rid of that check fail because we're not going to be check failing there anymore. So otherwise, we'll say while begin does not equal well, we better have enough bits remaining in the stream. So end minus begin must be greater than or equal to subpacket bits. And then while begin does not equal and well, actually we'll remember the end here. end of sub packets is begin plus sub packet bits. While begin does not equal end of subpackets, we will parse more subpackets. So instead of giving it the full end, I'm going to give it end of subpackets to, just make sure that we don't overrun the end there. Yeah, this stuff is going to be exactly the same. And then at the end of getting all these subpackets out, we will just say result.packet contents.inplace. And we'll move subpackets into there. And we will give it the type that it so desires. Standard vector, standard unique pointer of packet. Okay. So that I think that gives us the whole parse routine that we need here. And then what we want to do after the actual end is add up all the version numbers, apparently. So we'll say we'll add a method to packet called tree version, and start with the version of this, and then if the contents holds the alternative, which is a list of subpackets, then we will add all of theirs to this as well. For all the subpackets in that version of contents, we will add their tree version to that as well, and return that overall sum. So going back down here, now we just want to output the packets tree sum, or tree version, which is the sum of all those versions together. Let's go ahead and try and run this on our actual day 16 input now. It says 986. Let's see if that is correct. All right, that's right. So yeah, it took us a little while to write that binary parser by using just iterators over a vector of bools, but we got there. Okay, part 2. Now that you have the structure decoded, you can calculate the value of the expression it represents. The row values represent a single number as described above. Ring type ID is more interesting. Okay, so now we just need to calculate values here. Sum, product, minimum, maximum. Okay. Okay, this is actually going to be pretty easy based on what we want. We just need to write a value method for packet. So so we will switch on type. If it is 0, then it is sum. So we'll say I'm going to use auto to try and be a little less verbose here. I'm actually going to use the index to be a little less verbose as well, instead of using all the types, because otherwise I will lose my mind a little bit from trying to from trying to, just write out all the full types for everything. But then we just return the sum. So very simple, loop over all the subpackets, get the sum. Product is the product of everything, so very similarly, product, start with the multiplicative identity, which is 1. Multiply them out. Give our product. Case 2 is minimum. So we will start with the maximum passable value of uint64t. And then very similar loop here. Find the smallest. For 3, we have maximum. So just kind of flip everything here. So start with the minimum possible value, which is actually 0. And then max is max of max and the subpacket value, return max. 4 is a literal. So get 0 from contents, the literal value that's stored there. 5 is greater than, so it's 1 if the first is greater than the second, otherwise 0. So we'll just go ahead and check that that the vector in contents has exactly 2 elements. So we will say if the front value there is greater than the back value there, the first is greater than the second, then we return 1, otherwise we return 0. Case 6 is less than, so almost the same thing, just to flip the direction of the comparison. And 7 is equal to, so very similar to this as well. Just we use equal to instead of greater or less than. And there should not possibly be anything else there. Because we only use 3 bits to get this, and we've covered all the possible values. So that should allow us to recursively compute whatever value we need. So, and I realize that I haven't, that I've all been doing this in the same executable, so I'm just going to say part 1 and part 2 for this. Value. Okay. Let's run it. Okay. That is the value we get for part 2. Pretty big one. Let's go ahead and put that in there. And that's correct. And we just snuck in on the top 1,000, rank 906 on this star's leaderboard. So, this one, it's just about direction following and being able to, write a recursive algorithm, basically. And to, like, recursively, advance this. And, like, calculating the value and calculating the tree version is not that difficult. We used a variant to represent, the two kind of things. It can either be a literal or it can contain other packets. I think one thing that made this slightly difficult was the fact that I chose to do everything in terms of iterators on vectors of bools. If I had to do it again, I might try and abstract that complexity away and just have a kind of a bit feeder class or something that would just produce bits if it has any more left. But I don't think it's that bad, and it actually gives you kind of an idea of how STL style algorithms are implemented, because they all work in terms of iterators as well. So, and they're actually templated on the iterators that they take so that they're flexible and can be used with different containers. But yeah, I think, we still did pretty well here. So yeah, like I said, algorithmically, this isn't super hard. It's just, knowing to use recursion over stuff, but it's a matter of just applying all of the somewhat complicated instructions. There's quite a big wall of text with all the instructions describing this binary format. And the idea that, packets can contain subpackets and, you have a length ahead of time telling you, how much to expect. This reminds me a lot of some binary serialization formats I've worked with, in particular protocol buffers, even the variable length integers and stuff. There are some similar ideas in this, so I had a little bit of an idea of what I was doing ahead of time. But this vector of bools is not the absolute fastest way to write this, but it's still got us where we need to go. If this were real binary serialization, deserialization code, you would optimize it within an inch of its life. To make it as fast as possible, because you're going to be doing it all the time when it's going, back and forth on the wire, presumably to drive your planet scale web service or whatever. Anyway, though, thank you for watching tonight's stream. I hope you had fun with us tonight. As always, you can catch stream replays on my YouTube channel. If you're watching on Twitch, there is a link to the YouTube channel in my channel description there. And the GitHub repo where I upload all the code that we write is going to be either in the channel description if you're watching on Twitch, or just right down here in the video description if you're watching on YouTube. Thanks very much for watching, and I hope to see you again tomorrow night. Bye-bye.